thing that Rob Roy came up with a few years before. You know, you see a lot of synchronicity, except for his neck is too big, and the eyes look very human. And when I saw it, I tried, argued with him a little bit, and I said, Bill, you can't have human eyes in those eye sockets. He says, yeah, I know. When I tried to put the human eyes in, they stuck out like frog eyes. And I said, well, didn't that tell you something? He said, yeah, it told me I had to cut them in half to make them fit. And the same thing with the neck. He said, well, I only have human templates to go with, and I couldn't see that little bitty neck. But you can look, you can just see the muscles going out beyond where they really should go. This is what they really, it's more like that. But anyway, all that said, this is pretty cool. This is really pretty cool. And if you watch how he did it, it really is cool. And you'll see those neck muscles go on, and he'll expand them out. Yeah, pretty cool. Now, look around beside you. If you see anybody sleeping, wake them up, because I'm going to do it again, because it's really cool. Now, one of the things that people always talk about and people always ask me is, it looks so, human enough. Is it possible, would it be possible for for aliens to walk among us and not be seen, not be noticed? Well, it is possible. So if you see anybody that looks like this, let us know. Let us know. It could be. Okay, getting serious again. Two things in the star child skull are not found in any other creature on Earth. It has unknown fibers that are embedded in the matrix of its bone, and it has unknown red residue is in its cancellous holes. Now I'm going to explain that, but keep in mind, not found in any other species on Earth. All right? Now this is the cuts in the skulls for the DNA testing. We'll talk about that later. But the star child on the left, human on the right, just to again show you the difference in the thickness of the bone. And yet the star child is much harder. It's very dramatic, as you can see. So what we're going to be talking about is what got cut out of here and put under a scanning electron microscope. And when it was, they saw this and they said, well, what the heck are those? They are fibers buried in the matrix of the bone, pulled out by a Dremel blade. A Dremel blade is a blade, a high-speed blade used to cut bone out, and it would cut your finger off like it wasn't there. Probably cut your arm off. Dremel blade. They are bad news, and yet these fibers resisted the blade. Not entirely, but some of them did. Plenty of them. And when you look at this knot here, this is really amazing because you can see there are different kinds of these fibers. Now, first thought is, well, maybe there's something that grew on it, like molds or fungus or, bacteria, something. But you take it to a mycologist, as we did, took it actually to a group of them. They said, no, we've never seen anything like that. That you can see that's coming out of the matrix of the bone itself. You can see this one got caught in this one, which is a different kind, and sort of this wrapped up, but you see it tracks right through here and comes on up. And you can see kind of damage to it from the blade. These are hairs coming out of here, yet a different kind. And this is the third kind. This is a flat kind, and it was snagged on this rough piece of bone here, but look at the end of it, shredded. The Dremel blade did not cut through it like it would have done to my finger. It shredded it. My finger would not shred if a Dremel blade hit it. Okay? So, strong, very, very strong. It's like rebar in concrete to make that skull even harder than being tooth enamel. This is a hard skull. So, here's one of those fibers caught. We were just scanning around, and well, when they saw that, they said, hold on, go back to that. Oh my God, there it is. I mean, there is no better proof than that right there. In the matrix of the bone. Unknown in any other creature on Earth. Okay, now this is bones cut but not polished. When you run the Dremel blade, you see the marks of the blade, circular blade cutting through, you can see it. Well, this white stuff, this powder here, is the bone powder that the blade is chewing up and, kind of putting in the air when you cut. Okay, powder. But you can also break off pieces of the bone and polish them very carefully, like with lapidary tools, like jewelry. And this is what human bone looks like. It looks like alabaster. It's beautiful, really, it's beautiful. And these holes, this is the same hole, it's so big that you had to put it on two frames. But you see, each of these holes is crystal clear. Why? Because when you die, out in the wild, in the open, not the way we die, in the wild, in the open, Mother Nature cleans her plate. Because if she didn't, we'd walk out of this building and there'd be 1,000-foot high piles of bones. Mother Nature cleans her plate. And she does it with bacteria, fungi, mold, and she will break you down to your constituent elements in just a few weeks. It's really astounding how fast. They've done filmings of animals decaying, and it's much faster than they thought it would be. But one of the things that works on you is a kind of bacteria that eats out all of your bone marrow. Every single drop of bone marrow goes, and as you can see, this is what's left, is shining holes. You could eat out of those after the bacteria, they're so clean. Okay? With the star child, not so. You've got this stuff. We don't know what it is, but you got plenty of it. And it's not bone marrow, because bone marrow, when it oxidizes, it goes black. It's not that. We don't know what it is. But there's plenty of it. Now, we haven't had the money to do either the fibers or the red residue, because there are no protocols for recovering this sort of stuff. Nobody's ever seen it before. Nobody's ever heard of it. It's microscopic in size, very small, and it's very expensive to do all this. And once you got it out, then what test do you run? You don't even know what to do there. This is not to say it's never going to be done. As soon as we prove the star child is what it is, and it's okay for scientists to work on it. You know Otzi the Iceman, found in the Alps? Excuse me, surely you do. They've spent $30 million in the past few years on it, doing every kind of conceivable test you can imagine. They'll do the same sort of thing to star child when it's okay, when they have permission to do it from the higher authorities that run their sciences. So we haven't been able to do it. Why? There's another reason. It doesn't matter. It doesn't matter. Nothing we do from a physical standpoint matters to science. Nothing. I had one of these people that I talked to, and I was really challenging him and really sticking it to him and all that. He said, listen, I don't care if you stack up 10,000 of those differences. It does not matter. Why? None of the star child's physical differences means anything to mainstream scientists. They explain them all away with this line, which he said, nature can do anything. I have the perfect answer against you, which is nature can do anything. It can produce any combination you can throw at me. I can rally it right back at you saying nature can do anything. The only thing nature can't do is fool around with DNA. Only DNA impresses mainstream scientists because DNA is the math of biology. It's their tool. It's their favorite weapon. So what that means is we get to run them through with their own sword. Isn't that cool? Run them through with their own sword. Like 2 + 2 = 4. DNA says what it says every time with undeniable precision. If we make our case with DNA analysis, we will win, and we can make our case with DNA. We know that now. It's been a long, hard slog that I'm going to tell you about, but we can do it. All right, here's how it works. You have to start paying attention now. Put the thinking cap on for those of you who don't understand this. I'm going to make it clear. I'll go slow. Everything about the star child comes down to its DNA. All of the cells in our body, except the sex cells, blood cells, forget about that, 99.99, the cells in our body have the same thing. A nucleus with all of our chromosomal package that we receive from our mothers and our fathers. 23 chromosomes from mom, 23 chromosomes for dad, make a combination of 46 chromosomes. You with me? The chromosomes are made up of genes, about approximately 30,000 genes. They argue between 20 and 30,000. 30,000 is the high side, 20,000 is the low side, 25,000 is an average. Okay? Still not exactly sure. The genes are made up of the coiled strands of DNA. The coiled strands of DNA are made up of the nucleotides, A, T, C, G, to make these things, which are base pairs. Now, we'll see base pairs in a little more detail, so you have to understand base pairs. Base pairs are related genes. Thymine, adenine, guanine, cytosine. There are four nucleotides that make up everything that lives on this planet and probably on all other planets. Life is very probably ubiquitous, and it's based on these four nucleotides, which always combine with each other, these two together, to make what are called base pairs. And every gene has so many base pairs, and every chromosome has so many genes like that. You with me? Base pairs are important. Now, how does the base pairs work? How does DNA work? There is nuclear DNA and mitochondrial DNA, two types of DNA. Understand them. Mitochondrial DNA, this is a cell, like any cell in your body, and you have cytoplasm in here. Imagine just like jelly, and the nucleus is floating in the jelly. Floating within the jelly itself are these things which are called mitochondria, and they come only from your mother. Why? Because it's her egg that passes into you and becomes you. So her mitochondria becomes your mitochondria. As we all sit here today, we are carrying the same, basically, mitochondria as our mother, our grandmother, our great-grandmother, our great-great-grandmother, our great-great-great-grandmother, our great-great-great-great-great-great-grandmother. It passes down with very little change. And because of that, they are able to track back when the first of us began. And this is a little sidetrack. I'm sure most of you probably believe that it was some millions of years ago because we supposedly evolved from a common ancestor with chimps, and it broke off somewhere between 5 and 8 million years ago. But when they did the mitochondrial DNA studies in the mid to late 80s, they found that no, it didn't go back millions of years. It went back only 200,000 years. We don't exist as the way we are until about 200,000 years ago. Big surprise. Big war between the anthropologists who had the bones that insisted that it had to be done by evolution, and we had the geneticists saying, doesn't matter what you say, we've got the evidence here. And guess what? Because of DNA, because of the power of DNA, the geneticists have won. They just have beaten the anthropologists bloody. And so the anthropologists had to come back with, okay, Occam's razor at work. There must have been a bottleneck at around 200,000 years, and everything, all the humans, pre-humans died, except just this few little breeding pair, and everybody evolved from there at around 200,000 years ago. The bottleneck. I don't know if you've heard about it, but this is how the anthropologists explain what for them has to be true against what for the geneticists is true. Okay? So, the mitochondria, 16,000 base pairs in each one of these. A little more, 16,600, something like that. But just say 16,000. Keep the number in mind. Pretty good sized number, but not too big. Now, in the nucleus, because all the chromosomes, the 23 chromosomes from mom, 23 chromosomes from dad, when you put that together, you get 3 billion base pairs. 3 billion base pairs. Now we have that, we share that with chimps,